Welcome to example number 6, yet again, another measurement optimization problem. Okay, let's read through it and identify what the key parts of this question are. The council wanted to make a regular swimming area at the beach using a straight cliff on one side and the length of 300 metres of shark-proof netting for the other three sides. So what I've started to draw down over here is my cliff. What the question asks us to do, so that key verb is what. All right, so we're going to be giving another numerical answer. What are the dimensions of the rectangle that encloses the greatest area? All right, that word greatest, meaning largest. So the other way of saying that is a maximum. All right, so if we're thinking about maximums and minimums, these optimization problems, we are looking for a maximum stationary point. Okay, and then the other key part is we are doing it to do with the area of things as well. Okay. All right, so let's go down and let's draw our picture up. So we have the cliff enclosing one side and 300 meters, so a perimeter of 3, of shark-proof netting for the other three sides. So our perimeter is 300 meters. Now we have to give some values or pronumerals for these dimensions just so we can start to work algebraically with this. Now the next key part, I did underline it, regular swimming area, meaning not different sides, it's a rectangle. So we're going to have, let's just say x and y, and that means this opposite side here is also x. Okay? All right, so we have to think for our future answer about the area of things, but we're not given that perimeter idea just for any reason. It's a really good idea to start thinking first about using that 300 meter perimeter value. And this 300 meters of perimeter is equal to x plus y, otherwise known as 2x plus y. Yeah, so now we have an expression for the perimeter, and notice, remember, we're not shark-proof netting around the cliff, right? We're using that as a barrier, so we don't have to use as much shark-proof netting when we're making this swimming area. The next part of the thing, what the question is really asking us to do is find the dimensions of the rectangle that give us the biggest area, the greatest area, the maximum area. So now we just need to make an expression for area. And the area of a rectangle is the length times the breadth. Now, we have something we can use. So now we're almost doing like a simultaneous equation where I'm going to go to my perimeter formula above, and since I have got this singular y value there and the singular y value here, I'm going to rewrite this top expression to leave it in terms of y. So this means y is going to be equal to 300 minus 2x. Okay? So when I go and rewrite my area expression, I'm no longer going to write it as y, I'm going to write it as 300 minus 2x. Okay, so we can expand this and get ourselves 300x minus 2x squared for our expression for our area. Okay, so now that we have created our expression for the area of this rectangle that we're looking to maximize, we now have to think about actually doing the calculus work behind maximums and minimums. And of course, just like all the other questions, we're going to find stationary points, and we're going to be looking for that maximum stationary point. All right, and that is when the first derivative is equal to 0. All right, now we're finding the derivative of the area in this case. All right, so if we go and do this, we're going to be getting 300 minus 4x. and we're looking for when that is equal to 0. So we're going to get 4x is equal to 300, dividing by 4, x is equal to 75. So we have found a stationary point. This does not mean, or definitely mean, that it is a maximum stationary point. Okay, so for that we need to look at the second derivative. So let's go and do that now. Okay, so if we have the first derivative being 300 minus 4x, that means our second derivative is going to be just negative 4. Now this is less than 0, which means we have a concave down turning point, which means we have a maximum. All right, so therefore when x is 75, we do have a maximum. Right, it is going to be a maximum turning point. Okay, so we've now found the value of x in that scenario. Let's go find the value of y and finish this problem off. Okay, so I'm going back to the thinking of my very top of the page now, where I drew that nice little picture. Now when x is 75, y is 300 minus 2 lots of 75. Right, so 300 minus 150 is 150 metres. So to finish our question off, therefore the dimensions are 75 metres by 150 metres to produce the greatest swimming area. Now you could say that as to produce the maximum, but remember that word used in the question was greatest. We're kind of just highlighting that you need to think about what some of those other words might mean in the relation to these maximum and minimum problems. That's when these questions will be a tiny bit harder. All right, let's go on with question 7.